Welcome to Brain Vision.
Okay, so for this question, first we need to determine the enthalpies for the refrigerant 134A at different phase. Okay, so we know at the beginning the refrigerant was entering at 20 psia with a quality of 30%. Okay, so therefore if we use the table A12E at the back of the book, which is the saturated refrigerant 134A pressure table. So at 20 psia, we'll have the enthalpy of formation is equal to 11.436 British thermal units per pound mass, and the enthalpy of the evaporation is given as 91.302 British thermal units per pound mass. So now we can use the equation to determine the corresponding enthalpy for the refrigerants at the inlets, which is the initial enthalpy for the refrigerant 134A in this case, which is equal to HF plus X1 times HFG. X1 here is the quality of the inlets for the refrigerants 134A, which is 30%, which is 0.3. So eventually we'll have H1 is equal to 38.827 British thermal units per pound mass. So now let's determine the final enthalpy for the refrigerant 134A in this question, which is since in the question we're saying that it leaves as a saturated vapor at the center pressure. So we use the same table, which is A12E. So at 20 psia, we found that the enthalpy for the saturated vapor, which is Hg here, is equal to 102.74 British thermal units per pound mass. Okay, so now we can apply the energy balance equation. So we have E dot in is equal to E dot out. If we expand it, we have Q dot plus M dot times H1 is equal to M dot times H2. Okay, so Q dot here is the rate of heat transfer in the refrigerant 134A, and M dot here is the mass flow rates for the refrigerant 134A, and we know H1 is the initial enthalpy, H2 is the final enthalpy. If we do some arrangement here, we have Q dot is equal to M dot times H2 minus H1. So we know the mass flow rate for the refrigerant 134A is given as 4 pound mass per minute, which is equal to 1/15 pound mass per second. And then we know the initial enthalpy is 38.827 British thermal units per pound mass, and the final enthalpy is 102.74 British thermal units per pound mass. So now let's plug in back to the equation to determine the rate of heat transfer in the refrigerants, which is equal to 1/15 pound mass per second, and then times 102.74 British thermal units per pound mass minus 38.827 British thermal units per pound mass. Eventually, this will give us the rate of heat transfer in the refrigerants is about 4.261 British thermal units per second. Okay, so since the value here is positive, that means the rate of heat was transferred into the refrigerant. Okay, so if it's transferred into the refrigerant, that means the rate of heat was transferred out from the air. Okay, so therefore the rate of heat transfer of the air should be negative, which is negative Q dot, according to energy conservation law. Okay, so eventually you will have Q dot air is equal to negative 4.261 British thermal units per second. If we convert it to British thermal units per minute, it's about negative 255.7 British thermal units per minute. So now we can apply such equation here for the exit temperature of the air. So we know Q dot air should be equal to M dot A times Cp times Ta2 minus Ta1. M dot A here is the mass flow rate for the air, and Cp is the specific heat for the air. Ta2 is the final temperature for the air, which is the exit temperature of the air. Ta1 is the inlet temperature for the air, which is the initial temperature for the air. And we know the mass flow rate here, which is M dot A here, can be equal to rho A1 times V dot A1. Rho A1 is the density of air at the inlets. V dot A1 is the inlet volume flow rate and we know the density can be expressed as PA1 over RTA1. PA1 is the inlet pressure for the air, R is the gas constant for the air, and we know TA1 is the initial temperature for the air. Okay, so eventually we'll have such equation here for Q dot air. Okay, so if we do some arrangement here, we'll have TA2, which is the exit temperature of the air, is equal to TA1 plus Q dot air times R times TA1 over PA1 times V dot A1 times Cp. So we know the inlet pressure for the air is 14.7 psia, and we know the volume flow rate is given as 200 feet to the power 3 per minute, which is about 10 over 3 feet to the power 3 per second. And then we know the gas constant for the air is 0.3704 psia times V to the power 3 per pound mass times Rankine. And we know the initial temperature is 90 degrees Fahrenheit, which is 550 Rankine. And we know the specific heat for the air is 0.24 British thermal units per pound mass times degree Fahrenheit. So now let's plug in back to the equation to determine the exit temperature of the air. So the exit temperature of the air is equal to 90 degrees Fahrenheit plus negative 4.261 British thermal units per second, and then times 0.3704 psia. You know what, let me do this, because this unit here is kind of long. So let's do something like this. Psia times V to the power 3, and over pound mass times Rankine, and then multiply by TA1 at Rankine form, which is 550 Rankine. Okay, the reason why I use 550 Rankine in this part is because it's multiplied by the gas constant. I know gas constant has a unit Rankine here. So now we need to match with the gas constant here. So we'll have to use the 550 Rankine for the initial temperature. Okay, and then over 14.7 psia, and then multiply by 10 over 3 feet to the power 3 per second, and then times the specific heat for the air, which is 0.240 British thermal units per pound mass times degree Fahrenheit. And this will give us the exit temperature for the air is about 16.2 degree Fahrenheit. And these are the answers for this question.